Hello everyone, my name is Chandan Bose and today I'm going to present our work on combined effect of bluff-body shape and dual splitters on the flow-induced vibration-based piezoelectric energy harvesting. This work has been carried out in collaboration with Professor Abdulsattar Abdul Kafi from the New Mexico State University and Dr. Junlei Wang from Zhengzhou University. The primary motivation for this work comes from the quest of enhancing the energy harvesting potential from ambient environment. That can be from solar energy, that can be from the vibration of engineering structures, that can be the coupled fluid structure interaction dynamics of different engineering systems, or that can be from thermomechanical interactions or electromagnetic interactions. It is needless to say that the key focus of ambient energy harvesting is to produce continuous and sustainable low power supply to the futuristic engineering devices in order to reduce the carbon footprints, especially where there is less scope of changing the battery. Now, in this study, we will mostly focus on the energy harvesting from fluid structure interaction. The flow induced vibration based energy harvesting or fluid structure interaction based energy harvesting can be achieved from various aeroelastic phenomena such as vortex induced vibration, galloping, buffeting, or aeroelastic flutter. Our present work comprises of the combination of vortex-induced vibration and galloping. The conventional vortex-induced vibrations takes place in the flexibly mounted structures, often having a bluff-body cross-sectional shape due to the shedding of alternative vortices in the form of a von Karman wave, as it can be seen from this animation. The potential application of this conventional vortex-induced based energy harvesting can be seen in this futuristic design of bladeless energy harvesters, where we can achieve significant amount of energy from the intentionally driven vortex-induced vibration of these flexible chimney-like structures. It is pertinent to note that the conventional vortex induced vibration based energy harvesters are often limited to a finite range of flow velocities corresponding to the lock-in regime, where the resonance occurs due to the synchronization of the vortex shedding frequency with the structural natural frequency, leading to high amplitude oscillations in the structure. Therefore, there is a long-standing research work in this context happened on the scope of exploiting galloping to extract the flow energy for a broader range of flow velocity. Galloping is generally low frequency, high amplitude self-sustained limit cycle oscillations, which occurs for square cross-section bluff bodies in the contrary to the circular cross-section bluff bodies. And in the case of galloping, the amplitude of the oscillation monotonically increases with the flow velocity, which gives us the scope of extracting the flow energy for a broader range of flow velocities, and we do not have to depend on the constricted lock-in regime like the case of vortex-induced vibration. Now the question is, can we facilitate VIB to galloping transition through the innovative design of piezoelectric energy harvester? A limited number of recent researches have been carried out on this context to modify the surface structure of the energy harvesters in an innovative way so that it transitions from a vortex-induced vibration instability to a galloping instability. One such recent work has incorporated two Y-shaped attachment with a conventional vortex-induced vibration-based energy harvester, and it has been seen that due to these surface attachments and surface modifications, the harvesters transitions to a galloping regime, giving a broader range of flow velocity, significantly enhancing the energy harvesting potential. However, there are ample scope of improving this kind of designs, which is taken up in our present study. So in this study, we carry out low speed wind tunnel experiments and measure the output voltage and power of the structures in the presence of coupled fluid structure interactions. The schematic representation of the experimental workflow is presented here, and I would not explain it in detail as the time is limited. However, I would like to point out the fact that the range of wind speed that has been considered in this present study starts from 0.73 meter per second to around 3.6 meter per second. And these experiments have been carried out in the lab of Dr. Junlei Wang in Zhengzhou University. So, to investigate the transition from a FIV-based piezoelectric energy harvester to a galloping based piezoelectric harvester, we first investigate the effect of dual splitter attachments to a circular cylinder flexibly mounted with 1 degree of freedom, as can be seen in the left hand side. And we also investigate the effect of different length of these splitters and their relative angular positions with respect to each other to understand the transition mechanism from the vortex induced vibration to galloping, and to identify the optimal configuration for the maximum output voltage due to the coupled fluid structure interaction. In the next phase, we investigate the effect of bluff body shape on the harvested power output. To that end, we consider a square cross-section bluff body, and we similarly investigate the effect of dual splitters with different lengths and different angular positions relative to each other to identify the maximum output voltage obtained by an optimal configuration and compare that with the previous experiments of circular cross-section bluff body. Now, these are the experimental setups for these two kind of configuration with circular and the square bluff body cross sections. So to start with, we did the piezoelectric characterization of both of these configurations, and we found in both the cases the 1 mega ohm load resistance gives the optimal output power, and we also have determined the equivalent mass, damping, stiffness, capacitance characteristics, and measured the natural frequency of the structure in the absence of any splitter plate. So this particular case for circular cross sections is named as VIVPEH, vortex induced vibration based piezoelectric energy harvester, and with the cross section of a square we name it as galloping based piezoelectric energy harvesters. And similarly, we identify the equivalent system parameters. So these two cases acts as the base cases for our further investigations, including dual splitters. Now let us have an overview of all the experiments carried out for the VIVPEH with splitters. Here we can see that we have considered different length of the splitter starting from 0.4 times the diameter of the cylinder to the 2 times of diameter of the cylinder. And we also carried out experiments for different relative angular position of the splitter plates. So in this case, you can see the comparison of 30 degree, 60 degree and 180 degree angular positions. By comparing the voltage increase percentage and the power increase percentage, we found out that the 0.4 times the diameter of the cylinder length splitters gives the optimal energy harvesting performance, which is confirmed by the maximum amount of voltage increase and power increase in this case with a 60 degree angular position. On the other hand, for the square cross section bluff body configuration, we see that these performances changes significantly, and we see the maximum output power for the length of 0.8 times the size of the square d, and that happens for a relative position of 90 degree for the upstream case. To investigate it further, we compare the RMS output voltage for different angular positions for the FIV-PH with splitter. And we see that in the absence of splitter plate, a conventional FIV behavior is observed and we get a maximum output voltage of 2.37 volt, which also shows a constricted lock-in region. However, as we include the dual splitter with different relative positions, we see that at 30-degree relative position, the behavior transitions from FIV to galloping, giving a continuous increase in the voltage with the flow velocity. And we see the maximum performance at alpha equal to 60-degree, where we see suddenly the response amplitude jumps to a very high value and shows the galloping behavior. Whereas as we increase the angular position to 120-degree, we see that the structure stops to vibrate and the response amplitudes decreases to 0. And again, increasing the angular position further at alpha equal to 150-degree, we see the galloping behavior, however, with much lesser response amplitude. In the optimal configuration of alpha equal to 60-degree, you can see that the structure vibrates vigorously once the galloping phenomena starts, which in turn leads to high output voltage from the energy harvesting system. So this slide summarizes the effect of relative angular positions of the dual splitters on the maximum voltage output from the energy harvester. So as you can see that for the 60-degree angular position of the dual splitter, we get the maximum output voltage as 6.84 volt. Whereas in the absence of splitter plates, the output voltage from the conventional FIV-based energy harvester was 2.37 volt. And you can also see that in the absence of the splitter plates, we see a typical FIV kind of behavior, which has a constricted and finite range of flow velocities for the lock-in region. However, in the presence of dual splitter, that transitions to a galloping phenomena where we see a monotonic increase of the output voltage with the increase of flow velocity, which enables us for enhancing our energy harvesting regime for a broader range of flow velocities. Next, we compare the effect of bluff-body shape and the optimal relative position of the dual splitters for the FIV-based energy harvester and the galloping-based energy harvester. So if you can see that for 60-degree angular position, we get the maximum performance for the circular bluff body. However, at the same 60-degree position, we get much lower output voltage from the square shape bluff body and the galloping based energy harvester. So it clearly depicts the fact that the bluff body shape has a greater role to play to choose the relative position of the dual splitters. So we did a similar experimental investigation for a range of the length of the splitter plates with the square shaped bluff body and find that the maximum performance is achieved for the 90-degree angular position of the dual splitters instead of the 60-degree as was observed for the FIV based energy harvester. And we see that the length of 0.8 times the size of the square gives us the maximum power output due to the galloping phenomena, and it is achieved due to high amplitude and relatively lower frequency self-sustained oscillation. We also are currently investigating the underlying flow dynamics by high fidelity CFD simulations, and to that end we employ a two-way coupled FSI simulation strategy using the ALE approach. and we use the Laplacian displacement based mesh motion, and a partitioned weak coupling strategy is adopted. So this gives the mesh chosen for this study, and we observed that at the 180-degree position where a galloping phenomena is observed, there is a very interesting emergence of secondary vortices, as you can see, along with the primary coherent structure of the von Karman wave, which plays a great role to trigger this galloping phenomena. To understand it better, we compare different angular position of the splitters, and we see that at 0 degree, the position of the splitters regularize the flows, and we did not see any oscillation in the cylinder. However, for the 90-degree position of the splitters, we see big coherent vortex structures which gave a delayed vortex induced vibration. However, at the 180-degree position, we see emergence of very complicated secondary structures along with the big coherent vortices, and this plays a big role in triggering the galloping phenomena from the VIV. So to summarize, we can conclude that the use of dual symmetric splitters at different relative angular positions to the upcoming on uniform flow can enhance the piezoelectric energy harvesting from the FIV of the cylinder. And it has been shown that the different position of the dual symmetric splitters have a considerable impact on the energy harvesting efficiency, and an appropriate angle can lead to transition from the VIV vibration to galloping, which can significantly improve the energy harvesting performance. Further research is being carried out to understand the effect of the splitter length asymmetry in the relative angular position and the structural nonlinearity on the energy harvester's performance. For more details about this work, you can read our recently published letter in the Smart Materials and Structures. Thank you. And now I'm open to any questions you may have.